Folks, in the earlier video segments that I made for the analysis of composites using CATIA's native FEA solver, the problems were so simple that you could have compared the CATIA calculations against uh, the, the results of an AVD spreadsheet. Okay. However, starting buckling, uh, although these matrices are important, however, you cannot just get your answers by relying on a spreadsheet. You have to do a genuine FEA analysis. So what I'm doing now is a series of newer segments where you do a static analysis, and then we're going to follow it up with transient dynamics. By the way, the last one that I did dealt with finding natural frequencies of a composite structure or composite plate in that case. Even there, you had to do a genuine FEA calculation as opposed to just going to a matrix solver which handles ABD matrices. Okay, so here's the problem. This is our first one. Let me go ahead and what we're going to be doing is a static analysis of a composite plate that is clamped at all four edges. So let me go ahead here to my spreadsheet. Okay, so this sequence that we're going. Well, first of all, here's the problem. The plate, square plate, doesn't have to be square, but we're going to use a square plate, which is clamped at all four edges, is subject to a static pressure load. And what I mean by that is that this pressure, obviously, it has to be applied. It's going to apply so slowly that will not cause a dynamic response of the plate. Later on, we're going to be solving a problem like that where the pressure is suddenly applied, and therefore the plate is going to start vibrate, and that's a different story. It's the next video segment. Now, uh, the the geometry is taken so that it's consisting of four layers, plus and minus 45, symmetrically placed about that reference surface. And why I picked this particular geometry is that there are some results available in this book, and we're going to be comparing our results against that particular uh, uh, source. Now, the laminates are each 1.25 millimeter thick, so total laminate thickness of 4 times 0.0125, which is 5 millimeter, and the dimensions are given here. Okay, these are the material properties for graphite epoxy. Okay, and the applied pressure is 10 Pascal. Okay, and this is the table. This is the table from that source, from that reference, and the particular one that we're going to be looking at is all four edges are clamped, and the maximum deflection, static deflection, which is at the center, by the way, of the plate, is going to be 1.4 10 to the minus 6 meters. So we're going to be comparing our results against this. And although I'm not going to compare my stresses, but I'll remind you how to get the stresses, to be able to get the stresses in CATIA, and you can compare it if you want. Okay, so let's go ahead. The first thing I'm going to do is going to create my material property table. So let's go here. CATIA is running. So let's start with start infrastructure and material library. I'm going to make that material library, basically double click on this, and I'm going to call this thing static uh, problem plate, clamp plate. How about that? Clamp plate, so that I know exactly what uh, database I create. So it's going to be, notice that when I say apply, the name changes here. You go to composite, okay, and the thickness of it is 1.25 millimeter, right? So the cured thickness is 1.25 millimeters, okay. Okay, now notice that it doesn't round it off, but the number of precision of the thickness, at the display of the thickness is probably 3 digits. So it is actually that number that I inputted, but because of the display, it doesn't put more than 3 digits. If you want to change this thing, you have to go to your CATIA options and make the appropriate changes. But this is 1.25 millimeter, which is 0.00125 meter. Unidirectional, okay? And then we go to analysis, and we want to do 2D orthotropic, okay? So those numbers, E1 was 1.48 10 to the 11. If you go back here, it's this 1.48 10 to the 11 Pascal, or 148 GPa, okay? So I'm going to do it like that, 148, 48, big G, big P, big, or little a, so 148 GPa. E2 was 10.5 GPa, 10.5 big G, big PA, okay? Poisson ratio was 0.3, okay? And the shear modulus in all three directions, we're going to take it to be the same, and it's 5.61 GPa. 5.61 big G, big PA, okay? And then same thing here, 5.61 GPA and 5.61 GPA. Now, I don't need the density here, but in the next problem will be, or next video, that we're going to apply this thing dynamically or suddenly apply pressure. It's going to be a dynamic response, and we have to know the, 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 the density of this composite. Here we don't have to. And we say apply, and we say okay. I always have a habit of checking this analysis, make sure that nothing is mixed up, because sometimes I've noticed that sometimes I do this thing, and for some reason, maybe it has my carelessness, this turns into isotropic instead of orthotropic, and then when I try to run it, it won't be able to find it. It's a big mess. So we say okay. Now we're going to save this. I'm going to use this thing here, save as, and this is going to go into my desktop. I created a folder called static right there, and I'm going to give it a name that I can recognize. So I say static clamped plate, clamped composite plate. Okay, this is so that later on when I look at the stuff that's in my directory, I recognize what it is that I'm looking at. Now I'm going to finish this thing. So we're going to start with a part file. So we go new. It's going to be part file. Okay, and I'm going to call it uh, static static problem. Static problem. And we're going to make the geometry. The geometry is just a rectangle, which is half a meter by half a meter. So we go to generative shape design, and create a simple rectangle and dimension it. This one is what's the unit here? Oh, this is inches. I'm going to change these in a minute. So let me see. So this is going to be 0.5 meter. Same thing down here, 0.5 meter. Okay, exit, and let me fit it. But before I do the rest of the problem, I'm going to go change my units. Okay, okay, so we go to tools, options. Okay, under parameters and measures, units. So oh, this was meter. Okay, very good. So this was meter. Let me see. Fresh Pascal. Very good. I don't know why it showed me inches. Oh no, it's okay. All right, good. All right, we're set. Now we're going to put a surface through that, and the easiest way is to use the FIL, fill, FILL, through that. And I have a habit of joining, as you know. Double click on the join, flip this arrow down so that every time I put a shell element on the surface, the normal to the shell is in the upward direction. That normal is always opposite to the direction of the joint. I have a control over that. Okay, so this is pretty much it. The model is created. Oh yeah, let me also create a coordinate system here, which is going to be used as my rosette. So here is the axis system right there. See this right there, axis system. And I'm going to put my origin right now, but by default it puts it at the global origin, but I want to move this thing a little bit to the left so that this screen doesn't get cluttered. So I'm going to say right click, put the cursor here, right click the point, and the point coordinate of minus 30 centimeters in the y direction. So it shifts it to the left. You can see that right there. Okay, maybe minus 20. How about that? Minus 20 centimeter. That's better, closer. Okay, and then we say all right, so it puts the coordinate system right there. And I always uncheck this because I want to make sure that any XYZ that you use is referring to the global, not with respect to this one. Okay, so current, not the current. This becomes dashed, which means that any XYZ that you say is going to be not reference to this, but to the global coordinate system. So we save this thing, so file, save management. We put this file that I created, this part that I created in that folder, which was called static analysis. Very good. Okay, we're done here. Now we're going to go to composite design and composite parameters. This is where you specify material directions and stuff like that. Composite parameter, and we're going to add one. We go to the folder, that folder that I stored my database, material database. It was called statics, right there. And it was this thing, right? This is the material that I created. We select this and we say okay, and okay here. So there we are. And this is the cure thickness 0.125. Remember, we were just debating whether it was correctly inputted. Yeah, that was it. Now, as far as direction goes, we don't have to create anything extra because 45 and minus 45 are the standard ones. And rosette, we're going to add it. And it's this rosette that we created. Okay. Basically, this shows you for which directions these plies are. Okay. So if you don't like it, you can just, just what do you call hide this. Our problem is simple enough that we don't have to do something like this. Use that. Okay, so now we're going to create the plies manually. There's only 4 of them, so what I'm going to do is I'm going to do 2 and then use the symmetry to make the other one. So first thing you need to do is to create a ply group. Surface is right there. This is the surface. Draping direction, I have a habit of doing it upwards, okay? And this is it. Lock the plies draping direction. Very good. So a plies group 1 has been created. So my first ply, there's the ply. We're going to do that manually. It says which ply group is going to go into. There's only a single ply group that I created. The contour, what is the contour? Is contour I can select the sketch right there, select it. And the attribute, that's the correct material. And the angle, this is the first ply. And my first ply starting from one end is going to be, now we got to be careful here. When you talk about ply, this first ply, the first ply is actually the one that's closest to that surface, right? So that is minus 45. Okay. So that is minus 45. Okay, and say okay. And then the next one is going to be uh, plus 45, right? This one is, let me see, what did I put here? Check that. This was minus 45, so the one above it is going to be plus 45. So the next one, you click on it, you select the price group, and the contour is of course the same thing that you got picked before, and this is going to be plus 45. Okay, now you can look at the configuration that you have here. So where is apply exploder? Right there. Apply group 1. So it goes like that. And I noticed that does Mac does agree with yeah. So this agrees with those colors. Now, if you don't want it in this form, some people prefer this one. Okay, that's what I had. You say cancel. Now we're gonna, instead of me doing two more manually, I'm gonna use this icon here, which is symmetry right there, symmetric ply stacking. It says, what's the group? Well, obviously there's only one group here. And the meaning of non-pivot means that, you see I have two up here, reflect them down, so two down below. So it's going to be basically four, two on top, two below. But if you say pivot, what it does, it assumes that one of the plies that I created, that green one, was it was not repeated. So there's going to be red, green, red. Okay, that's what pivot is. I don't want it. I want it to be red, green, green, red. So I don't want to pivot. You say okay, and then you can look at your ply group, see whether it's what you want or not. This is what I wanted, right? Right there. See that? Okay, if I had pivoted it, then it would be green, red, and green. Okay, so cancel. All right, so save everything. This is all done. And now we're going to go to our generative advanced meshing tools, because I want to get my usual nice quad type of elements here. So you select it. This is a static problem, and you mesh it. You select that surface, and I want this. I want 5 centimeters. Okay, so remember this thing was 50 centimeters. I want 5 centimeters, the size of the element. Okay, so there's going to be 10 in this direction, 10 in that direction. That gives you a total 100. And then, of course, there is parabolic. These are parabolic elements that I'm using. Okay, you say OK, and then you click on this icon, which is meshing it. What I just did was specify the mesh size. I did not mesh it. So you click on this thing to mesh it, and right there you say OK, and we are exiting the advanced meshing tool. Okay, so now we're going to go to generative shape design right there. And if you want to look at your mesh, that's easy. You put the cursor on that, nodes and elements, right click mesh visualization, and it shows you what you're looking for. Now, I don't need the mesh. I deactivate that. Okay, because with that mesh being present, you cannot apply the load, or you need the geometry. Now, the other thing I want to do is I want to hide my stacking sequence here, hide it, and I want to hide my sketch. The reason is that later on I want to put a clamp on the edges. With that sketch being there, it won't be able, it won't be it won't let me take these edges, or with the plies being present, the edges are covered with those plies. It won't let me take it. Okay, now let's go ahead and do this. Well, first of all, these edges are all clamped, so I select the clamp on this and that and that. Now the clamp means that displacement and rotations are fixed. Okay, and we apply pressure here. Pressure is right there. Pressure on that. I'll put down 10 Pascal, right? That's what we had, 10 Pascal PA. What did I type here? Let's try it again. 10 big P little a. That should work. Okay, good. Or you could have done 10 Newton per meter squared. Same thing. Now, if I run it now, it's going to complain. Let me run it and show you why it's going to complain. So let me run it, because there's something I haven't done. It says, hey, I don't have the properties of this thing that you gave me. In other words, uh, 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 if in the case of a regular shell, you need the thickness, 2D property, but in the case of a composite, you have to go here. This is what it was missing. You go and import composite properties, okay? Just because you created it in that composite design workbench doesn't mean it understands it doesn't go to the finite element. So you have to import it. Okay, so the surface is right there. And for the method, we don't have zones here. There are two ways of doing it. We have only ply here. I didn't create zone. So by ply, you click on the wrench and you go and select that ply group that you created. So you select this, it's going to take all of these and it's going to do its job. And we want it to be symmetric, this stack up, to be symmetrically placed about that reference surface. Remember that I showed you here? I want this thing symmetrically be placed about that reference surface. Okay, that's pretty much it. Why don't we save our analysis? So file, save management. This is the analysis, save as, and on purpose, I'm going to call this, give it a different name. I'll call it static. So that later on, if I have a whole whack of things in that folder, I know what corresponds to what. And we say, okay, very good. And now we're going to run it. Okay, let's look at the, first of all, the deflected shape. That doesn't surprise you. This is correct. If you want numbers, you have the numbers. Double click on it. If you want the average ISO so that it looks nice and colorful, it's right there. And look at the maximum deflection, 1.4 e to the minus 6. And let me take you to the right there. This is the center deflection according to that source reference, 1.4 10 to the minus 6. So it's working. Now, as far as the stresses go, I just wanted to, I'm not going to compare these. I didn't have the time to do that. So I'm just going to show you how to get it, and then you can go ahead and dig it out yourself if you're interested. So let me deactivate this plot that I created. Now notice that when it comes to composite, it won't let you plot things or the usual way. If this was a isotropic problem, then this icon would not be dim. You can actually plot the von Mises stress. But in the case of composite, a von Mises stress by itself doesn't make sense because the question is stress where, what ply. So it has to be done on a ply by ply basis, and therefore they won't let you do it like that. So the trick, if you look at the earlier, I don't know, 20 videos, you see this thing repeatedly done. You put the cursor here on static case solution. You put the cursor here, right click, and you say generate image. Generate image. It says, what do you want? Well, I want the stresses. So I filter it out according to the stresses. Otherwise, you have to go search and find all the stresses here. And for example, if you look at the full stress component, tensor component, you say, okay, all right. Now the question is, what am I plotting? So you go here, you double click on this, you expand this more. It says that you are plotting uh, C11, and C11 is your sigma x, okay? The only problem is that this is with respect to the local coordinate system, and local coordinate system I can't rely because I don't know whether it's actually aligned with x or aligned with y. So to avoid that, I'm going to choose a global coordinate system. So notice that you click on this, you change your or any coordinate system that you want, and then it's CX, okay? For what layer? This is laminar number 1. Okay, remember you start from the bottom, you go one by one up. So 1 is at the one extreme end, then it's the next one, and then above it, and then above it. Okay, so laminar 1 will be uh, this one. Okay, this will be laminar 1, laminar 2, laminar 3, and laminar 4. I bet 3, 1 and well, obviously they're not going to be the same because this is bending. Okay, so let's see now. Just to convince you, this is looks like sigma x. Now you really have to go and dig that out yourself. So and the question is, where is this thing plotted? So you yeah, this requires a little bit of closer inspection, but what I do is I check the displacement, and displacement, they match pretty good. And then to find out exactly what is it that you're looking for, you have to be a little bit careful here, and we're not going to be able to do it on this video. So by the way, let me see now. This is lamina 1, and remember this point is roughly 10,000. If I go to lamina 4, okay, which is the bottom, the very bottom, notice that it switches down here, okay, because one goes into tension, the other one is going into compression, and therefore the sign flips, okay. That's pretty much it. In case you want to plot the von Mises stress at different layer, you select this, okay, and uh, there's the von Mises at layer 4. Now, if you look at layer 1, it's going to be identical. See, layer 4 is this number. Layer 1 is going to be identical. Yeah, identical. 3.26, 3.26. Okay. Well, have fun. The next one is going to be doing the same type of problem, although I'm going to change my numbers here. I'm going to use a different material, the loading, although it's uniform pressure, but it's a different value, because I want to be able to compare it against some other sources. Okay, this particular reference did not have the dynamic result in it. Okay, have fun.